Here's an example of 3 isotopes that you may or may not have heard of, and these are fairly common. These are the 3 isotopes of hydrogen. Hydrogen has 3 main isotopes, and the first one is called protium, and that's like regular hydrogen. Now, look at the symbols on the left-hand side. Protons for hydrogen must be 1. So the lower left-hand number in all of those is 1 because it's hydrogen. Hydrogen always has 1 proton. But you can see the upper number, which is protons plus neutrons, goes from the top at 1 to the middle at 2 to the lower part at 3. So the top part, if it's a mass number of 1, that's protons plus neutrons. And if we subtract the protons, which is 1, that means this first one here has 0 neutrons. And that's called protium. Protium is by far the most common form of hydrogen. It's 99.9 some percent of all the hydrogen, stuff like that. Very, very common. When you drink water, most of the water, which has hydrogen in it, is protium. Now, the next one, though, is maybe one you've heard before, too. Now, this one has a mass number of 2. So 2 minus 1, that's 1 neutron. This is a heavier version of hydrogen, and the official name is deuterium. But the unofficial name is heavy hydrogen. Heavy hydrogen is sometimes used in nuclear experiments, or you hear about it and stuff like that. Check out the ice glass on the right-hand side. Normal ice, which is solid water up there, floats on the water. All right, no problem. The ice is less dense. If you have deuterium ice, which by the way would be kind of expensive, but it is kind of cool from a science perspective. But anyway, let's say you had D2O. So that's also H2O with hydrogen, but it's the deuterium version. It actually sinks. It's more massive. The density is greater. It sinks to the bottom. It's really, really cool. But anyway, I digress. Now, there is a third isotope of hydrogen called tritium, and this one with a mass number of 3 minus 1, it has 2 neutrons. This isotope is radioactive, and believe it or not, every time you take a drink of water, you've got some super, super, super small amount of tritium in the water. And it's normal. It's nothing to freak out about or anything. Our life is naturally acclimated to a little bit of radiation around us all the time. You get a little radiation when you go in an airplane, for example. So don't let that freak you out. But it is something that's around us a lot. If we had like 100% tritium, we would be in trouble as human beings. But fortunately, it's very, very small. So anyway, hydrogen has 3 isotopes. And again, I would argue that all the elements have multiple isotopes, at least in some combination. There's lots of uses for isotopes. All right, there's lots of scary ones, which is all the nuclear energy and stuff. But this is a cool example. This is an example using something called technetium-99. Technetium is number 43 on the periodic table, and they can use it to create a type of a mellow gamma ray. And the gamma rays can actually help medical doctors see what's happening in your body, the soft tissues and stuff like that. Apparently, they use this up at OHSU here in Portland, but I haven't confirmed that. This is a mass spectrometer, kind of a diagram here, and this is how they figure out the isotopes. Now, in the lower right-hand corner is a graph, and notice here how there is a boron 10 and a boron 11, and to the right-hand side, there's a chlorine 35 and a chlorine 37. And how the mass spectrometer works is you put your sample in, and it gets vaporized, which means just really small particles. And then they also will usually shoot some kind of electrons at it, and the electrons end up making some very positive ions. This is an example with neon in this picture. And they can change the force of the magnet, like bigger, smaller, and stuff like that, and it separates out the different masses. So in the picture, there's a neon 20, a neon 22, and a neon 21. And the magnet is aligned just right so that the neon 21 is the only one that goes through the detector. So you end up with graphs that look like this, and we're also seeing them down below, which is kind of a cool thing. So think of this as like a super powerful bathroom scale for elements, all right? It's able to figure out like how much you have and stuff. Also, though, I want to point out, for boron, notice here how the boron 10 is a much smaller amount than the boron 11. Boron 11 is a lot taller, all right? So if the boron 11 is considered considered 100, then the boron 10 there, it looks like, is about 25. So not all the isotopes are around us in equal amounts. And I already talked about how most of hydrogen is the protium, the simplest, a little bit of deuterium, and a super, super small amount of tritium. Most of the isotopes exist in multiple amounts, and we'll talk about that in a little bit. The other part of the periodic table we haven't talked about yet was the number with lots of sig figs usually, and that has different names, but right now let's call it the atomic weight, all right? Now, boron, we saw in the last slide, there's a lot more boron 11 than there is boron 10, and the atomic weight is kind of the average of all of the different isotopes. And when you find an average in chemistry, you take essentially like the decimal amount of it around. So like there it says 20% boron 10. The decimal version would be 0.2 and the 80% would be 0.8. You take those numbers and you multiply them by the masses. And if you then add that together, that gives you the overall weight. This is statistics in a very zero level kind of discussion. So let's say we wanted to estimate the atomic weight, which is basically the average of all the isotopes. Boron has boron 10, and that's where that 10 comes from, and there's boron 11. And if you take the 20% and you divide by 100, you get 0.2, and if you take 80% and divide by 100, you get 0.8. So in your calculator, 0.2 times 10 plus 0.8 times 11, it comes out to be 10.8. And that's how they find these atomic weights. And if you look on your periodic table right now for boron, it's going to be a number about 10.8 as well. There's a lot of periodic tables that are better than this calculation. You'll have more sig figs, but this is how they get those numbers. So it's the mass of the isotope times its decimal percentage plus the mass of the other isotope times its decimal percentage. You add those together to get the overall weight. So all of those numbers are experimentally derived, all right? They do change every once in a while. They'll go through this major changes to the periodic table because they have better values for mass. But now you know the secrets of how those numbers come out. Notice that 10.8 is not the 10 of boron 10 or the 11 of boron 11. That's an independent number, and that's going to be important to us. Lithium has two main isotopes. The lithium 6 is about 7.5, and the lithium 7 is about 92.5. Now, if you look on the periodic table, my particular one right here for lithium, the atomic weight 6.941, and yours might be a little different, better, worse, and stuff is fine, but this is how these numbers come around. So the atomic weight is 6.941, and notice that it's closer to the lithium 7 than 6, like 6.941. Here, let me write it in here. This is kind of cool. I can do this. Anyway, 6.941 in my periodic table is much closer to 7 than 6. Like if I rounded up 6.9, it would be 7. That's because most of lithium is lithium 7. If this would have been 90% lithium 6 and only 10% or so lithium 7, then the atomic weight would have been closer to 6, maybe like 6.1 or something like that. Silicon has several isotopes, and you can see though right away that silicon 28 is more than 90% abundant, which means more than 9 out of 10 times you're going to have a silicon 28. And if you look on the periodic table, you'll get a number something like this. My periodic table lists 28.09. Again, yours might be a little different. And again, because the most abundant isotope was silicon 28, it makes sense that the atomic weight, which is basically an average, will be closest to that as well. Here's a problem. You've got 3 different isotopes, all right, 72, 73, and 74, and it's some random element E, okay? And the question is, which of these is the most reasonable atomic weight? And you can see there's 72.1, 72.8, 73.4, 73.8, 74. Okay, so when I see a problem like this, I start off by looking for which isotope is most abundant. And you can see that the most abundant one is definitely 72. So the atomic weight is going to be closest to 72 because it's the most abundant, all right? However, it's not like 90% abundant. Like with the silicon, we saw like a 90% made the abundance close to it. This is only 50%. And we do have a pretty good amount of 74 and 73. So let's start here. I don't think it would be 74. All right, that's out because it's not 100% the 74 isotope. That doesn't seem reasonable. And because it's more than 50% 72, I would cut out those as well. I don't think that's very reasonable. However, it's not like 90% plus of the 72 isotope. I don't think it's going to be 72.1 either. If the isotope 72 was like 90%, then I could maybe see a 72.1, but it's just a little more than 50%. I'm going to argue that answer B is the most reasonable, all right? And that certainly is what it should be and stuff. So because isotope 72 was more abundant, it's going to be close to 72, but because it wasn't like 90% abundant, probably not 72.1, but somewhere not too far from there. Nitrogen has two main isotopes, nitrogen 14 with a mass of 14.0031, 99.6299%, and nitrogen 15, 15.001 AMUs, 0.3701%. We're using a lot of sig figs here, and that's what people do when they calculate the numbers you see on the periodic table. So from these two, we can calculate the average atomic mass. And again, what we're going to do is we're going to use the decimal version of those percentages and multiply it times the isotope mass, and we'll add that to the same thing for the other isotope together, and that'll give the average mass. So what we have right here, 99.6299% divided by 100, 0.996299, and we multiply it by the mass of the isotope, 14.0031. Now the other one was 0.3701%. So that number divided by 100 is an even smaller number, but we'll multiply that by that isotope mass. And we'll add these two things together. If you do this, 14.0068 AMU. And if you look on your periodic table, that's not too bad. Now, my periodic table, which honestly is a little cheesy at this point, 14.01. So this is a much better sig fig value. 14.0068 has much more sig figs than 14.01. Mine's not bad or anything like that, but obviously you can do better. Gallium has two main isotopes, gallium-69 and gallium-71, and the average atomic mass, 69.723. We can use this information to calculate the percent abundance of each isotope. And this is kind of an interesting problem. Now, first of all, I want to talk about what's happening right here. And to talk about it, I want to use a number line. Now, a number line, it can be really helpful with these kind of problems. And on my number line, I'm going to have 69 and I'm going to have 71. And that's because those are the two isotope mass numbers that we're dealing with. But in addition, the halfway point would be 70, and you can see that the average of all these, which is what the atomic mass is, 69.723. Now, this average, which you can see on the number line, is a little bit closer to 69 than it is 71. And that's useful to us because that's going to tell us, if we've done this problem right, that the percent of 69 is going to be greater than the percent of 71. Now, it's not like super close to 69.7. I mean, it's not far away, but it's not super close either. So it's not going to be like 90% 69 and 10% 71, but we can use this kind of information to at least make the suggestion that the isotope of the 69 gallium will be a greater percentage than the isotope of the 71 gallium, or gallium-71. To solve this, it's not too bad. What we can do is set up our equation so far. And remember that you take the decimal version of the first isotope, which we don't know, I'll call it X, and you multiply it by the mass of that isotope. Then you add it to the decimal version of the other isotope, which we don't know either. Let's call it Y. And you multiply it by its mass, that number, and that equals the average, which is the atomic mass. So you can see right now we have two unknowns and one equation. We don't know X or Y. And really, to solve equations in math, you need to only have one unknown in an equation. So we need another relationship that somehow is going to break our two unknown variables. And because we have only two isotopes, the two percentages together have to equal 100%. So if you had 50% A and 50% B, that would be 100. Or if you had 90% A and 10% B, that would equal 100. And we only have, in these types of problems, two percentages. 1, which would be the decimal version of 100, equals X plus Y. So Y, we can substitute in then 1 minus X. And that's what we're going to do on this next slide. We're going to put 1 minus X in there for Y. Then we have only one unknown, X, all right? We can solve for it. We can get all the X's on one side, all the numbers on the other side, solve for X. Then we'll come back to this equation I circled. 1 minus that number, 1 minus X will equal Y. And remember, X and Y have to be positive numbers less than 1. So here's the X and the Y, and here I substituted in the 1 minus X for it. So what we want to do here is we want to solve for X. Now, I skipped some steps here, and I'm going to let you try this problem on your own. But if you want me to get you a little bit farther, you can say here that 69.723 equals 68.9257x. That's basically these two right here. Plus, you're going to use distributive property, which means 1 times the 70 number, 70.9249. And then I'm going to go minus X times that, minus 70.9249x. So now my handwriting is sloppy, but you have two X's. First X minus the second X will give you just so many X's. Then you can subtract the 70 number from 69.23. You'll have X's on one side, numbers on the other side. If you did that right, X 0.6012, which again times 100%, 60.12%. And if you go back to the other equation, 1 minus X would be 0.3988 or 39.88%. Now, this is a good time to step back and see if this all makes sense. Earlier, we said how the abundance of the 69 isotope must be larger than the 71. The average, 69.7, is closer to 69 than it is 71. And you can see that's what we got. We saw that it's about 60% 69 gallium 69, and it's about 40% gallium 71. So all this is fitting in place. This is a cool way to check yourself on these calculations if you're ever uncertain. Try this on your own. And of course, if you get stuck, this is a good thing to email me, take a screenshot of what you're doing or a picture on your phone, whatever, and say, oh, I need help, I'm stuck. And that's when I can help maybe you to figure out how this all works out. It's a cool technique. It only works when you don't know the abundance of 2 isotopes. It doesn't work if you have 3, etc. Antimony, Sb, number 51, has 2 isotopes. First isotope, about 121 at 57.20%. Second one, almost 123 at 42.80%. Average atomic mass, 121.7. And this question is important. Will you ever have one atom of antimony with 121.760 AMUs? And the answer is a resounding no. You are not, if you have a big bag of antimony, you start pulling out antimony atoms and you can somehow magically figure out their masses automatically, you'll never have a mass of 121.7. 57.20% of the time, you're going to get an antimony with 120.9038. And 42.80% of the time, you're going to get an antimony with 122.904. Remember, the 57.20 is almost 60%, which is like 6 out of 10. 42.80 estimate is about 40%, about 4 out of 10. So 6 out of 10 times the 120.9 and 4 out of 10 times roughly 122.9. But you're never going to have 121.76. The 121.76, the numbers you see on the periodic table, are statistically generated numbers. And in the United States, sometimes they'll say that the average family has 2.5 kids, all right? But if you've ever gone to like anybody's house in the United States and you go up and you knock on the door, you won't see 2 regular kids come out and some kind of like half kid come out, which is just gruesome and morbid. And I apologize for the bad imagery, but you don't see that. You'll see houses with 2 kids and houses with 3 kids and houses with 1 kid and houses with 4 kids and houses with 0 kids and houses with 5 kids, but you won't see like a half kid, all right? That's just repulsive. Anyway, statistically generated numbers are artificial, all right? Like you won't have a family with 2.5 kids, you'll have families with 2 and 3. And 121.76 is the same as the 2.5 kids. It's an artificial number. You'll never have one atom with that mass, all right? There is a use for that mass, and it's a super cool use, as we're going to see. But for right now, I want to be very clear. You're never going to have one atom with that exact mass.
When magnesium metal burns, the product of the reaction has a greater mass than that of the original magnesium. John Dalton's atomic theory successfully explained this seemingly strange result.
We have to have a way to count atoms, all right? People in the old days would take a piece of magnesium, burn it in air, and they would create magnesium oxide. Magnesium oxide is kind of like a white powdery kind of stuff, this stuff here at the bottom. And the magnesium itself is a very fine kind of metal. And people studied the ash relative to the metal, and they saw that the ash had more mass. And these pictures right here, the left-hand side is magnesium, and the right-hand side is a magnesium oxide. It's MgO. We'll see later how that's happening. But if you don't know how much oxygen to add to the magnesium or magnesium to add to the oxygen, you're going to get yourself in trouble. So chemists need what's like a counting unit so that we can add like one correct amount of oxygen to react with our amount of magnesium. And it's a really cool kind of tool that people have developed. So in science, the counting unit that chemistry uses all the time is called the mole. Woohoo, the mole is so cool. Anyway, the mole is not the little dude that runs around in your grass if you have it and like makes holes and stuff. Those are sometimes gophers, by the way, too. But anyway, the mole in chemistry is similar to the idea of a dozen. And if I said to any of you, hey, go get me a dozen donuts, you'd probably have no problem going to the store and getting me 12 donuts because a dozen is 12 and 12 is a dozen. But you could also get a dozen roses or a dozen cans of Coke or a dozen coffees, whatever kind of thing works it out. You don't have to actually think about it as 12, but it's a counting unit. And of course, 2 dozen would be 24, twice 12. Half a dozen would be 6, etc., etc. The mole is really similar to the dozen. Mole was first named by this guy Ostwald in 1893. It had been proposed by a guy named Avogadro, but Ostwald was the one that thought of the name the mole, which is kind of cool. Speaking of Avogadro, Avogadro was apparently a very shy mathematician, and you can see the dates there a long time ago. But anyway, he was the one that first proposed the idea for a number. And now we call this number Avogadro's number. Sometimes it gets the symbol N, big N sub A, but that's one anyway. Avogadro's number is a really important number in chemistry, and this is the full version, 6.022140776. It goes on for a longer, times 10 to the 23rd. I really want you to know / memorize 6.022 times 10 to the 23rd. We're going to use that number a lot. And if you have to keep looking it up all the time, that's going to be a real drag on your time and kind of annoying. So if you know 6.022 times 10 to the 23rd, that's awesome. And this number refers to the number of units in a mole. So if you're talking about copper, an element, that would be number of atoms of copper in a mole of copper. If you're talking about a compound, for example, CO2, the smallest piece of a compound is a molecule. So a mole of CO2 would be 6.022 times 10 to the 23rd molecules of CO2. So again, that 6.022 times 10 to the 23rd, kind of a weird number, but it is like a dozen, like 12, all right? And 12 is a dozen, and a dozen is 12. Well, 6.022 times 10 to the 23rd is a mole, and a mole is 6.022 times 10 to the 23rd. If you have exactly 12.00 grams of pure carbon-12, and pure carbon-12, by the way, is hard to get because there's other isotopes with most carbon, but if you have exactly 12 grams of pure carbon-12, then you're going to have exactly 6.022 times 10 to the 23rd atoms of carbon. And they call this 12-gram number the molar mass. It's 12 grams of carbon in 1 mole of carbon. And this is only for pure carbon-12, by the way. Now, all of the isotopes of carbon makes the mass a little higher. If you look on the periodic table, the mass is going to be a little bit bigger number. Mine is 12.01. Here I use 12.011, and you can get into better values. That's just because carbon isn't pure carbon-12. There's also carbon-13, a little carbon-14. But all of those numbers on there, on the periodic table, those are molar mass numbers. They're also called atomic mass numbers. We'll talk about that in a little bit. But the main use that we're going to use in Chem 221 through Chem 223, molar mass. It's the grams of that element in a mole. And we'll talk about this. If you have pure carbon-12, that's 12.00 grams of that, 6.022 times 10 to the 23rd. And all the isotopes together would be 12.011. So all of these molar masses, or as they're also known, atomic weight, and either way is fine, they're all listed on the periodic table. So aluminum on this periodic table here, 26.9815. My aluminum is 26.98. That's okay. You can get, of course, better and worse ones, but it's the other really important thing on the periodic table. So again, all good periodic tables should have the atomic number, that whole number. They'll have the symbol for the element. So 13 protons is aluminum with the symbol Al, but it's also going to have this number, which is called atomic weight or molar mass. And we're going to see they're the same number with two different uses. Here's a type of a problem you might see. It says, what's the molar mass of an element with an atomic number of 12? So I'm making you think about what these different things mean. An atomic number, if you remember from earlier, that's not the molar mass number, that's the number of protons. So if you look on your periodic table, atomic number 12 is magnesium, Mg, and it's the other number on your periodic table, which is what you want for this answer. Now, for my periodic table here, Mg is 24.31. If you had a better periodic table with more sig figs, it'll be a number better than that. But you can see that the answer here, which is closest to 24.31, is D, 24.3050. So atomic number means number of protons. That's magnesium on the periodic table. And that 24.3050 is the other number that's listed on the periodic table. These are all 1 mole amounts, all right? Sulfur, magnesium, tin, and silicon. So the copper that the person is holding, copper, if you look on the periodic table, about 63.546. So that person is holding 63.546 grams of copper. The sulfur on the far left, sulfur is about 32.07 on my cheesy periodic table. Yours is probably better. So that's about 32.07 grams of sulfur. And there's magnesium, 24.3-ish grams, tin, etc., etc. The densities of the elements are different. So that's why sulfur looks like it takes up the most volume, but all of them have different densities. Copper is a pretty relatively high density, so it takes up less volume. Oh, it's all coming together. So here's a problem you might see. What amount of magnesium is represented by 0.200 grams, and how many atoms is it? Now, if you have a small piece of magnesium that has a mass of 0.200 grams, it would literally fit on the pinky of your hand. All right, it's a very, very small amount. It doesn't look very impressive. But let's figure out the amount of moles, all right, using the molar mass. And with a good periodic table, magnesium 24.3050 grams. So I'm only going to use 24.31 here. And this brings up a good point. Chemists are always obsessed with sig figs. This is a 3 sig fig number, and you never want the molar mass to limit your sig figs. So if I use just 24 here, that would be bad form. You could use 24.3050, but it takes more time to enter in your calculator or make the little graphic like I did. So you always want to have at least 3 sig figs going forward. I used 4 sig figs here, so I cut 24.3050 down to 24.31. Most of the time, using a molar mass to the hundredth, which is 2 decimals to the right, places to the right, is enough sig figs, but that's just a rough guide. Regardless, you can see here that those numbers on the periodic table are grams per mole, starting with the grams, 0.200 grams. Grams on the bottom and grams on the top cancel. In your calculator, 0.200 divided by 24.31, you get a number. It's going to be like that. Round it to 3 sig figs, 8.23 times 10 to the minus 3 moles. And again, we're rounding it to 3 because the top number is 3 sig figs. I used a 4 sig fig, 24.31. The final answer has to have the smallest number of sig figs, 3. And again, you could have used 24.3050. That would have been fine. It just takes more time, but either way is okay. Now, 8.23 times 10 to the minus 3 is not a very impressive number. I don't know what that means. That doesn't mean anything. It's a smallish number, but I don't know. But the next part is kind of cool. How many atoms are in this piece of magnesium? Now remember, a dozen of anything is 12, and a mole of anything, 6.022 times 10 to the 23rd. So we're going to take that mole number and multiply it by Avogadro's number. We're going to turn moles of magnesium into atoms of magnesium using Avogadro's. So if you take that mole and you multiply it by 6.022 times 10 to the 23rd, the moles on the top cancel moles on the bottom, still limited to 3 sig figs because our Avogadro's number had 4 sig figs, and you get the incredibly large 4.96 times 10 to the 21st atoms of magnesium. And I want you to step back for a second and think about that number. 10 to the third is 1,000. 10 to the 6th is 1,000,000. 10 to the 9th is 1 billion. You have more than 1 billion, 10 to the 18th atoms in that little tiny bit of magnesium that fits on your pinky. All right? These atoms are so small, they hardly take up any space at all. And just a small amount, in this case of magnesium, has just an enormous number of atoms. It's just crazy. So think about these numbers as you go through. They're astronomical, how big some of them are. And as you eat a piece of cake, or if you drink some of my beloved coffee, all right, you're consuming just an inordinate amount of atoms at any one time. And that's what happens in our day-to-day life. It's just amazing. But anyway, Avogadro's number, the key to figuring it out. Notice we went grams to moles to atoms. You always want to go through that step. You could also go atoms to moles to grams. You could go the reverse step, but you wouldn't go grams to atoms directly. You have to go through the moles. Let's say that I have 3.011 times 10 to the 23rd atoms of pure carbon-12, and the question is, how many grams of carbon-12 do I have? Okay, so I'm starting with atoms this time, and I want to get to grams, so I'm going to go atoms to moles to grams, the opposite, like we just talked about. To go atoms to moles, I'm going to use Avogadro's number, and from moles to grams, I'm going to use carbon's number. And since it's pure carbon-12, that means it's exactly 12 grams per mole. So mathematically, you could take the number of atoms we're given with divided by Avogadro's, 6.022 times 10 to the 23rd. But notice if you divide by that number, the 10 to the 23rds cancel out. 3.011 divided by 6.022 is half, all right, 0.5000. That's the moles. And then half of a mole times 12 grams per mole is how you can find the answer. Now, if that was too weird, here's the worked out answers. First part, here's the number we were given. We're dividing by Avogadro's number to get the moles, and it's exactly half, 0.5000 with lots of sig figs. Then you go moles to grams using the molar mass. Pure carbon-12 is exactly 12 grams per mole, so that means we have 6.000 grams of carbon-12, or answer C. Mendeleev was the first one to develop the modern periodic table. We talked about him briefly in the chapter 1. He thought that the elements had properties which had patterns to them, and he was correct. He thought it was better to have the functions of their atomic weights, like their masses. And so the first version of Mendeleev's periodic table was based more on mass. Later on, though, scientists figured out, and that's what we're using right now, that it's better to use a periodic table based on atomic numbers. You see the period properties, which we'll talk more later, better through the atomic number than through the mass number. But Mendeleev was cool. He figured out a whole bunch of new elements before they'd been found. So Mendeleev was seen as a pretty cool way. So the periodic table has changed over time. Periods on the periodic table go left to right. So in this animation, the red represents a period. The first period is hydrogen and helium. The second period is lithium on the left through neon. Third is Na, sodium through argon. Fourth is potassium, K through krypton, etc., etc. Notice on this periodic table, hydrogen is listed both on the left and the right. Sometimes hydrogen acts more like an atom on the left in group 1A, and sometimes it acts more like it is right here on the right. We'll talk about this more later, but just realize hydrogen is kind of flexible. Now, I mentioned group earlier. Periods go left to right. Groups go top to bottom. Groups are going to be really important to us. And the way that this animation is set up, it lists the common designation for groups. Groups 1A and 2A are on the left. And you can see on the right, we have groups 7A through 8A. All the A groups are called the main group metals and nonmetals. The elements in the groups in the middle all have B's by them. Those are called the transition metals, or the lanthanides and actinides. They have a different kind of reactivity than the A groups do, and that's what we'll see. So the A groups are main group elements, main group metals and main group nonmetals. The B groups are the transition metals. Oh, there's also some rejected elements in the periodic tables. Bear with me. Some of these are just totally silly and stuff like that. Here's Clorox, which I won't make any jokes about. Asparagus, which I actually like and stuff. You can see that some of them are criminal elements. Some of them are owned by Microsoft. All right, stupid. Just joking. Anyway, sorry. Maybe I'm not sorry. I don't know. Anyway, periodic table then again. So you got the A groups and the B groups like we talked about. Underneath is a set of lanthanide and actinides. Depends on your periodic table again. Lanthanides are usually like 58 or so to 71, and the actinides, depending on your periodic table, 89 through 103, depends on your periodic table once again. But they're just different types of metals, different types of elements. Now, most of the periodic table, like we said in chapter 1, is metals. Everything to the left of the green line is a metal, with the exception of hydrogen in the upper left corner. The yellow ones in the upper right and hydrogen are the nonmetals, and there are a series of elements in the middle, the green in this one, that are called metalloids. They have some properties of metals, some properties of nonmetals, and we'll see in the future sections what it means to be a metal and a nonmetal more. We'll talk about some of these more than others, but I want you to hear these names so you're starting to get familiar with them. Some of the groups have important names. Alkali Metals is group 1A. And again, we're going to use the A groups in this class a lot, but there is another alternative designation you can see in this periodic table. Group 1A is also group 1. I call the number systems the international version of the periodic table. It's the same thing, but the 1A, 2A, 8A has a lot of use for us, so we're going to use that predominantly. Anyway, group 1A or group 1, they're the alkali metals. And right next door, group 2A or group 2 are the alkaline earth metals. And those are different groups, and they're both important, and they're both going to pop in. So remember, group 1A, alkali, group 2A, alkaline earth. Now, there's several groups that have kind of cool names, but we won't use them that often. Group 3A, the fancy name is Icosagens, but I'm going to call them once in a while twisted metals. And I'll explain in later lectures why I call them that way. That's an unofficial name. It's something you have to use, but there is some reason why group 3A is kind of twisted. Group 4A is a real mixture of nonmetals and metals, like carbon on the top and lead on the bottom. So you got some really wild properties. Crystallogens is their fancy name, but again, nobody uses that except nerdy instructors like me. Group 5A, Pnictogens, another name nobody hardly used. That apparently has something to do with to choke, phosphorus, arsenic, stuff like that. Bad news. Group 5A. Chalcogens, chalk formers, are in group 6A. Again, that's an informal name too. Oxygen, sulfur, selenium, etc. Now, another one I do want you to know, halogens. Halogens is group 7A. That's chlorine, bromine, iodine, fluorine. Very important. And the noble gases in group 8A are also important too. Those are on the far right. So please know alkali metals, alkaline earth metals, halogens, and noble gases, but the rest of them you can totally ignore. So, which list of elements contains an alkali metal, a pnictogen, and a halogen? Alkali metal, group 1A, pnictogen, group 5A, halogen, group 7A. And I'll let you explore this one on your own, but if you look at that list long enough, it's answer E. Rubidium is an alkali metal, group 1A at the bottom. Antimony, we talked about earlier, is a group 5A pnictogen, and astatine is a radioactive halogen.
The main engine of the NASA Space Shuttle is fueled by the elements oxygen and hydrogen. A huge amount of energy is required to lift the shuttle into orbit. When mixed and ignited, the fuels produce water and a large quantity of energy.
Hydrogen is the simplest of all the elements, but is by no means the least important. And hydrogen is super important for so many things. And the primary way that hydrogen is used is like a source of energy. It was used in the space shuttle when the space shuttles were going. It's also used a lot in the rockets that are used to get things into space. It's a real powerful kind of tool. It's very flammable. In 1939, a German air balloon crashed over New Jersey at the Hindenburg, and this is a picture of it right here. At the time, the Axis and stuff, this was pre-World War II, they would use these balloons, because hydrogen's a lot more abundant in Europe than it is in America. We have a lot of helium, which is non-flammable. But anyway, something happened, a lot of controversy, it burst into flames, bad news. If you're a fan of Led Zeppelin, and of course I have to have bad movies and bad music reference every chance I get, Led Zeppelin 1 actually is a picture of the Hindenburg crash. So again, it's just hydrogen kind of out of control. Oh, this is kind of a cool thing. This just happened. In January of 2017, scientists in Germany think they discovered and were able to create metallic hydrogen. Hydrogen is over on the left side, and I said it's a nonmetal, and most of the time in our class, that's what we'll think of it. However, if you pressurize hydrogen, it can act like a metal, and this group in Germany thinks that they found it. They've always postulated that metallic hydrogen is in the core of Jupiter and things like this, but they were able to make it in a lab, which is pretty exciting. So I expect to hear more about metallic hydrogen coming out. Group 1A, the alkali metals, are very soft metals. They include sodium, potassium, lithium, stuff like that. You can literally cut these metals with a knife. It has to be a dry knife All these metals react very intensely with water. And I encourage you on YouTube to explore like sodium with water or rubidium with water, stuff like that. It's very exciting. But as long as the knife is dry, they're very, very soft and stuff, which is cool. Lots of uses for alkali metals we'll see.
Here's rubidium. Rubidium in water reacts much more violent than potassium. Rubidium again. So as we go down the alkali metals, they become more and more reactive. So now let's take a look at the next metal, cesium.
Notice the energy that's given off there by rubidium and cesium with water. It's amazing. Rubidium was pretty powerful, but cesium actually blew the container out. You must be very careful. And even sodium and potassium, when they're pure, will do this. You don't find any of these metals naturally at room temperature and pressure at these conditions, but you can make them in a lab and then use them.
When magnesium metal burns, the product of the reaction has a greater mass than that of the original magnesium. John Dalton's atomic theory successfully explained this seemingly strange result.
Alkaline earth metals are also very reactive, although not as reactive as the alkali metals. Magnesium, calcium, very important to us, very important to the things around us. Fireworks have a lot of alkali metals, barium, strontium, stuff like that. They all occur naturally in compounds except beryllium, which you can get. So just like the alkali metals, the alkaline earth metals usually have reacted. They're in compounds, but in the lab, you can then make pure magnesium, pure calcium, stuff like that. Group 3A, icosagens, or what I'm going to call twisted metals for reasons I'll explain later, are kind of fun. Aluminum is a very abundant metal, all right, used for a lot of things from drinking cans to aircraft and all kinds of stuff. Boron from borax and things has a lot of uses. Gallium's kind of fun. Gallium is a metal at room temperature and pressure. However, it has a very low melting point. So if you place gallium in your hand, it actually melts. It turns into a liquid and stuff right away. And there's jokes about liquid spoons and stuff like that you can look up online. Very cool. I'll talk more about the twisted metal parts in future lectures. This group also includes, of course, indium and thallium. Indium has a lot of uses for different things. Thallium is a really interesting poison. And if you're into forensics and forensic chemistry, lots of interesting stories about people poisoning with thallium. Very interesting. Group 4A has a whole bunch of different elements. Carbon and silicon are more nonmetals, while the lower ones, tin, SN, and lead, PB, are more metals, and GE, germanium, kind of right in between. Carbon, obviously, super important to us for life, but it's also used in diamond and graphite and things like that. Silicon, transistors, and semiconductors, stuff like that. Also, sand has a lot of silicon. Lots of uses for all of these elements. The pnictogens are group 5, again a weird name. Nitrogen and phosphorus, so important for farming and agriculture. Arsenic has a lot of uses, antimony and bismuth. Very cool kind of things. Phosphorus has a couple different forms. Some of it's used for like really bright lights, like in the military, but again, it's also used for different our agricultural things. One compound with nitrogen I want to point out is ammonia. And ammonia, NH3, is something we're going to use quite a bit. You've got to know what ammonia is. So ammonia is NH3 and NH3 is ammonia. Ammonia has a lot of similarities to water, H2O, and we'll explore those as we go through, but it will help you if you know that water is H2O and of course ammonia, NH3. Now, phosphorus was actually discovered in a time where I consider science of chemistry to be more of alchemy. Alchemy is like a pre-version of chemistry. And this guy named Brandt, who was looking at urine one day, and alchemists were fascinated, in my opinion, basically by things that were gold. They thought they could make gold into it. And they were also fascinated by the ultimate solvent. But what do you hold it solvent in? But anyway, I digress. So Brandt was looking at his urine and thought, all right, gold. I must be some gold in my urine. So he did a lot of work with urine and he didn't find any gold, but he did discover phosphorus. And that's kind of cool too. So most chemist jobs these days aren't so demanding. You don't have to analyze urine samples over and over. Trust me, it's Just babbling. All right, chalcogens, group 6. Oxygen, of course, important for breathing. Sulfur, sulfuric acid, which is a big part of agriculture. Selenium, you need a little bit in your body all the time, important. Tellurium, polonium, also cool too. Lots of uses for these different things.
The reaction of sodium and chlorine is a vigorous one. We use sand to protect the flask from excessive heat. Then, we fill the flask with chlorine gas. Next, we add sodium. And then a few drops of water to activate the reaction. The reaction produces sodium chloride.
In this video, it shows the reaction between sodium metal, the soft metal we talked about earlier, with chlorine gas. Chlorine gas has kind of an off yellow color if it's high enough concentration, but it's pretty hard to see. What's really interesting in this reaction is that sodium metal, which reacts really violently with water, if you put that like in your mouth, it would explode. It would really hurt and might kill you. It'd be really bad news. On the other hand, you put chlorine in your body, chlorine would kill you too. It was a nerve agent in World War I stuff. It really did chemical warfare kind of stuff the Germans used. But the fascinating thing is sodium metal and chlorine gas, things that will kill you, combine with a lot of energy released. You saw the orange flame come off there and stuff. They combine to make table salt, sodium chloride. And I bet all of you have used table salt already someplace. Like it's in a food you ate, or maybe you put some on French fries or something. So a lot of times the properties of the compounds we make quite different than the properties of the pieces we put into it. But anyway, the halogens make this possible. Fluorine, chlorine, bromine, iodine are the four main ones. All right, they're very important. Astatine is radioactive. There is one more. It's tennessinium, TS. Very, very rare, but another brand new player on the block. Most of the time when we think of halogens, we think of just fluorine through iodine because those are the most common. And they're very important halogens. We'll see lots of uses for them coming out. Group 8A, the noble gases, are also fascinating. People used to call Group 8A the inert gases because no compounds had ever been made with them. But in the late 50s, early 60s, scientists came out and were able to make compounds with several of them. And this is one of them right here, XeOF4. They also made some other compounds with xenon and some compounds with krypton. So people don't call this group the inert gases anymore because they're not so inert. Now they're just called the noble gases. Now helium is also really abundant in the universe. It's really important. Neon, argon, also very important. Krypton, no relationship to Superman's krypton. Darn it. Xenon in some headlights for cars. Radon is something that affects a lot of people in Portland. People do radon tests on their house. Radon comes from radioactive processes deep in the earth up through your floor, basically, and into your house. So they try and figure out if there's any radon stuff around. Transition metals, lanthanides, actinides, also really important. This is actually the area that I did most of my research in, and I'm very fond of all of them. Iron is probably the most famous, well, maybe gold or silver, but iron makes rust, which is iron 3 oxide, kind of interesting. Lots of uses for these different transition metals. But the reason I went into transition metals is because of the colors, and this silly slide here shows many of the colors that you can get. Now, several of the first ones have chromium. So there's a blue and a yellow and an orange. And then there's a couple of manganese. So this is manganate on the kind of left, which is bluish, and permanganate kind of a purplish on the right. And then you can see here iron, iron 2, and iron 3. Some of them don't have any colors, which is cool. Here's a couple different cobalts and coppers and nickels. There's lots of color in transition metals. And I'll be honest, that's the reason why I went to inorganic chemistry. I was just fascinated by the colors. In organic chemistry, you will often have white, sometimes black, and if you're unlucky, brown compounds. All right, and that's about it, man. Brown is unlucky because it usually means that it's been oxidized. The air got into it. White is very common, sometimes black and stuff with white. So with the brown one. So I really liked the colors of transition metals. You can just see basically what a dork I am. Anyway, that's it for Chapter 2, Part 1. Like with all the chapters, there is a study guide, which is a bulleted list of the highlights from this section. There's a concept guide, which is a series of worked problems from this section. So if you have any questions, check those out. Following these slides in the printed version, you can see some of the important equations from this particular section, and there's also some end of the chapter problems with the answers. And I encourage you to go through those, make sure you know how they work before you, and if you can do them, then you've got this section down. Okay, that's it for Chapter 2, Part 1. Good luck with your studying, and if you have any questions, let me know. I'm rooting for you.